Welcome to SysAdmin. In today's explainer, we're going to explore foundations of layered network architecture and protocol hierarchies. Whether you're just stepping into a brand new IT role, managing a massive enterprise environment, or trying to track down those incredibly elusive bugs in a server room, understanding exactly how networks are built, literally layer by layer, is absolutely critical. Honestly, this architecture is the invisible backbone of everything we do in cybersecurity, system administration, and networking. So let's dive right in. Here is our roadmap for today. We'll cover the purpose of layers, the rules of communication, the anatomy of this architecture, the journey of a message, real-world sysadmin applications, and then we'll wrap it up with a quick summary. All right, Section 1, the purpose of layers. Let's look at why we actually use them. It really is the fundamental question, right? Why do networks even need layers? Well, imagine trying to build the entire internet, or honestly even just a basic local office network, as one single massive piece of software. It would be an absolute nightmare to design, let alone fix or upgrade. So the real magic here is that layers exist to drastically reduce that design complexity. By breaking this massive problem of communication down into smaller, bite-sized pieces, we make the whole system incredibly functional and, most importantly, scalable. In a layered architecture, networks are organized sequentially, just stacked right on top of each other, like a tall building. Now, the exact number of layers, their names, and what they actually do can totally differ from network to network depending on the specific model you're looking at. But the absolute golden rule across all of them is this. The fundamental purpose of any given layer is to offer specific services to the layer immediately above it. It essentially shields that higher layer from all the messy, complicated details of how those services are actually getting done under the hood. Moving on to Section 2, let's talk about the rules of communication, otherwise known as protocols. At its absolute core, a protocol is simply an agreement. It's an agreement between communicating parties on exactly how their communication is going to proceed. When Layer N on your laptop carries on a conversation with Layer N on a web server halfway across the world, the rules and conventions they use to actually understand each other, that is the Layer N protocol. If they don't agree on that protocol up front, the data is literally just meaningless noise. To make this mutual agreement work flawlessly, every protocol breaks down into three key elements. First up is syntax. Think of this as the grammar. It's the data format, the coding, the electrical signal levels. It's what the data actually looks like. Second, we have semantics. This is the meaning behind the data, including control information and error handling. Basically, what does the data signify, and what on earth do we do if something breaks? And third is timing. This handles speed matching and sequencing. It ensures one machine isn't blasting data way too fast for the other to handle, and that everything arrives in the exact right order. Okay, Section 3, architecture anatomy. Let's see how we actually stack these layers together. In our source material today, the standard network model we're looking at is built on a 5-layer architecture. We've got layer 5 sitting at the very top. That represents the application level, which is closest to you, the user. And that stack goes all the way down to layer 1 at the absolute bottom, which handles the raw physical hardware transmission. Now we need to draw a really vital distinction here between network architecture and implementation. The network architecture is the visible set of layers and the specific protocol stack being used. It's the public face, what the outside world sees and interacts with. But the implementation, that's the underlying code and the precise software specifications running deep inside the machine. That part is completely hidden. It's not considered part of the architecture, and it's totally invisible to the outside world. Within this setup, we have what are known as peers. Peers are simply the entities that make up the corresponding layers on different machines. So layer 5 on machine A is a direct peer to layer 5 on machine B. A great way to think about this is using a corporate ladder analogy. When the CEO of one company wants to negotiate a deal with the CEO of another company, they're communicating as peers, right? They're agreeing on the high-level business logic, even if they aren't the ones actually typing up the contracts. But obviously, those two CEOs don't just physically shout across the city to each other. They pass the actual message down their own corporate ladders. In our network architecture, this downward passing happens through interfaces. And an interface exists between every single pair of adjacent layers, like right between layer 5 and layer 4. And that interface clearly and strictly defines which operations and services the lower layer is offering to the upper layer. Because the reality is, no data magically teleports horizontally from layer N on one machine directly over to layer N on another. That just doesn't happen. Each layer passes the data and the control information down to the layer immediately below it, crossing those interfaces until it hits rock bottom.
And below layer 1 lies the physical transmission medium. We're talking copper cables, fiber optics, or Wi-Fi radio waves. That is where the actual physical transmission finally takes place.
Section 4, the message journey. Let's trace a message from top to bottom. This perfectly illustrates the concept of encapsulation. It's like working on a shipping assembly line. It starts at the top. Step 1, the protocol entity in layer 5 produces a message. Let's just call it M. Step 2, this message gets passed down to layer 4, which slaps a header, H4, onto the front of it. This header is packed with essential control info. Step 3, the message goes down to layer 3. Now, layer 3 often has to chop the message up into smaller units called packets. So our one message becomes packet M1 and packet M2. Layer 3 then adds its own header, H3, to each of those individual packets. Step 4, layer 2 gets these packets and adds not just a layer 2 header, H2, but also a trailer, T2, at the very end to close it out. Finally, step 5. These fully packaged, wrapped up units are handed to layer 1, where they're converted into raw physical signals and blasted across the wire. And then, when those signals finally reach the destination machine, the exact reverse process kicks in. We call this de-encapsulation. Layer 1 receives the physical signals and hands them up to layer 2. Layer 2 reads and strips away that H2 header and T2 trailer, then passes the clean packet up to layer 3. Layer 3 reads its routing data, rips off the H3 header, and passes the pieces up to layer 4. Layer 4 reads the sequencing info, carefully reassembles the original message, drops the H4 header, and at last hands the pure original message right up to layer 5 for processing. Now, through all of this wrapping and unwrapping, there is an incredibly strict technical rule regarding data boundaries. Headers and trailers from one layer are never, ever passed up to the layer above it. Ever. Layer 4 has absolutely no idea that Layer 3's headers even exist. It's on a strict need-to-know basis, and this total separation of duties is exactly what keeps the whole system stable. Section 5, SysAdmin applications. Let's look at some real-world uses. So why do we care? Well, the practical relevance for us is immense. Whether you're managing real day-to-day networks, configuring web servers, locking down enterprise environments, or sweating through an emergency troubleshooting scenario, you are constantly interacting with these layers. Think about it. If users can't reach a vital website, is the server software crashed up at layer 5? Is a firewall port blocked at layer 4? Is the IP routing completely misconfigured at layer 3? Or did someone literally trip and unplug the physical cable down at layer 1? Understanding this hierarchy gives you a roadmap to troubleshoot methodically, either top-down or bottom-up, instead of just randomly guessing and hoping for the best. And here is a perfect real-world example of why this modular design is absolutely brilliant. Because of those clear interfaces between the layers we talked about, a sysadmin or a developer can completely rip out a layer's underlying implementation and drop in a brand new one without breaking the overall architecture. For instance, you could physically swap out a whole copper network for a fiber optic network down at layer 1. And guess what? Your layer 5 web browser doesn't need a single line of code changed. It doesn't even notice. The interface guarantees that the upper layers remain completely blissfully unaffected. It's a total game changer. Finally, Section 6, Summary and Takeaways. Let's wrap this all up. Our source material actually leaves us with a rather famous and, frankly, pretty fun mnemonic to help anchor these network layers in your memory. Please do not touch Silva's pet alligator. Now, while our specific walkthrough today focused on a 5-layer model, this classic memory hook is used by IT students all over the world to remember the flow of data architectures. It's a great reminder that no matter the specific model you're looking at, layers are always structured sequentially and logically. So, to quickly summarize our core technical takeaways for today, network layers exist primarily to drastically reduce design complexity. Protocols are those critical agreements that allow peers to communicate, and they rely on strict syntax, semantics, and timing. Always remember the vital difference between the public, visible network architecture and the hidden, interchangeable implementation code. And finally, data never teleports. It travels down the stack via encapsulation, crosses the physical medium, and is de-encapsulated at the destination, strictly respecting the interfaces between every single layer. I'm going to leave you with this final thought. If developers can completely swap out a layer's hidden implementation without breaking the entire network, which layer's underlying mechanics actually fascinate you the most? Is it the raw physical signaling of the hardware, the complex maze-like routing of packets, or maybe the application layer serving the end user? Have a think about that the next time you look at your own IT infrastructure.
If you found this helpful, subscribe to SysAdmin Academy and continue building your IT expertise.